Okay, so for our final project, we designed and conducted simulation on three components, namely an upright, a hub, and a wheel center. However, for our project, we only conducted and listed the simulations for two of these components, namely our upright and our wheel center. The primary design factors in our component designs were to keep components as light as possible, while at the same time achieving a minimum factor of safety of at least 1.3 in all scenarios. Another primary concern was to keep machining costs low. Alrighty, so here are three of the design iterations for our wheel center. We had 10 design iterations, but we included three of them. Here's our iteration 1, iteration 5, and iteration 10. Below are listed the free body diagrams. The green circles represent where the fixed restraints are applied, and these pink lines represent where the remote loading originates and where it is applied to on the wheel center. We conducted four different driving we accounted for four different driving scenarios for both our wheel centers and our uprights, and they included 2G longitudinal acceleration, which you see in this first free body diagram plot, 2G longitudinal braking, 2G steady state turn, and the 2G bump. Here is a table of results for our wheel centers. And here's a stress plot along with a curvature based mesh model to see the size of our elements, basically resulting in an even transition of stress colors on the stress plot. Here's a factor of safety plot denoting with the red areas denoting where maximum stress occurred. And here's a picture of a design insight tool plot which we use to remove material in non-critical locations. We also conducted a modal analysis. Here are the first two resonant frequencies pictured. And basically for our modal analysis, we used the results and they played a part in us designing the wheel centers to be fixed around the inner three lug holes. For our rear upright, we had three design iterations pictured, even though we conducted 5 design iterations. So here's the initial one, an intermediate one, and our final design iteration. Free body diagrams, same as wheel centers. We used green to denote where the fixtures are applied. So there's 3 holes at the top and 2 holes at the bottom where tabs are going to be mounted, to which control arms and our push rod attaches to. And these pink arrows represent where the static load is applied, replicating the contact of a bearing on the inner races of the upright. We conducted simulation on 4 driving scenarios, same as the wheel center. Namely, the first one being 2G longitudinal acceleration, the second one being 2G longitudinal braking, the third one being 1.8G steady state turn, and the last one being a 2G bump. And here's also a table of results, along with a stress plot, curvature based model, another factor of safety, and a design insight tool plot. We also performed a combined analysis, and so what this entailed was basically that because during operating conditions our upright will see a uniform 140 degree temperature Fahrenheit during operating conditions, we accounted for this 65 degrees temperature by changing 2 material properties in 6061 T6 aluminum in SolidWorks, namely the yield strength and the tensile strength. And then we used, here's a table of results to compare the values of factors of safety from our final design of our upright at 75 degrees Fahrenheit and at 140 degrees Fahrenheit. And here are the factor of safety values. We also considered the fatigue analysis. The fatigue analysis results are pictured in the following figures. Here's one for the first scenario, namely 2G acceleration. Here's one for 2G braking, and here's one for 2G bump. You can see the stress concentrations in each of these. The table of results for these fatigue analysis basically show the amount of cycles that the component will endure until failure. And here's an SN plot. And so basically we learned, in the conclusion, the software simulations trying to replicate these physical scenarios hold many parameters ideal and don't account for less than theoretically ideal physical conditions. So we basically created a less conservative approach by deriving numbers for theoretical conditions that our car won't actually achieve. So for example, our car won't actually achieve 2G acceleration or 2G braking, but that's what we accounted for. From physical testing, we saw that it only reached up to 1.75 G's acceleration, but we don't mind a less conservative approach in order for us to have factors of safety that are actually true and viable. We hope you enjoyed our presentation and take a look at our report to see a more in-depth view at each of our scenarios. Thank you.